So, it gives me great pleasure to welcome you all to the first Keynote paper, and in particular, it gives me great pleasure to welcome the first Keynote speaker, Professor Maria Heckl. Now, Maria was graduated in physics at the Technical University of Berlin and completed a PhD in 1985 on heat sources in acoustic resonators in the engineering department at the University of Cambridge. And that means she was one of a long line of distinguished acousticians who've had the pleasure of being supervised by the late Sean Folks-Williams. She progressed from being a lecturer in applied mathematics at Keele between 1992 and 2000, via being a senior lecturer in 2001 to 2013, and eventually was Professor of Engineering Mathematics in the School of Chemical and Physical Sciences at Keele University. She's gained a total research grant income of over £10 million. She's published over 80 articles in journals and conference proceedings, and has a patent on reheat buzz control. She's President-elect and Director and Fellow of the International Institute of Acoustics and Vibration, IIAV. She serves on the editorial boards of the Journal of Sound and Vibration and of the International Journal of Spray and Combustion Dynamics. Her research interests are in physical acoustics with technical applications, in particular noise control, instability control, and non-destructive testing. We've heard a bit about equality, diversity, and inclusion earlier today, and Maria is passionate about gender balance in scientific research. And she's also passionate about research that benefits the environment. And this latter passion relates to her talk today, so I will ask her to give it. Thank you.
Thank you very much, Keith, for your introduction. And also thank you very much to the organizers, and in particular to Barry Gibbs for inviting me to this special occasion. I'm very pleased and honored to be here. Right, the title of my talk, as you can see on the screen here, is Sustainable Combustion Technologies Need Acoustics Research. That is not the most obvious statement to make. In fact, it's an assertion. And the aim of my presentation is to give you the evidence that this assertion really is true. And here we have an overview over my talk. So it's divided into four parts. The first part is introduction and background. In the second part, I will show you an analytical way of modeling combustion instabilities with a technique involving the Green's function. In the third part, I will show you some results that have been obtained with this Green's function approach from my group, past and present. And finally, in the fourth part, I will draw some conclusions. Right, so introduction and background first. Right, well, sound plays a very important role in combustion instabilities. And to illustrate that, let's consider a generic combustion system, which is depicted at the top of this slide here. We have an acoustic resonator, which is marked in this black line, sort of in cross-section. It has a kind of inlet tube and an end, and a flow, which is a mixture of fuel and air, comes into this resonator and feeds a flame. So we have a flame sitting here, and the flow is sort of enters the combustion chamber like a jet, so you get vortices forming and flow, more generally flow perturbations sort of in this area of the combustion system. And of course, we also have sound waves because we have an acoustic resonator. And these sound waves play a very important role in what can go on in such a combustion chamber. First of all, the sound waves can interact with a flame. And what happens is that a sound wave disturbs a flame. That means the heat release rate from the flame oscillates, and the flame acts as an acoustic source. But vice versa, acoustic waves in the resonator affect the flame, and the flame responds to those sound waves. So there is this feedback between the flames and the sound, or the flame and the sound, and this feedback can lead to a vicious circle where the heat release rate amplitude amplifies the sound amplitude, and in turn, and so on. And this feedback mechanism is called a thermoacoustic instability. I actually want to demonstrate this here with a very simple demonstration. It's called the Heckl tube, which is the most sort of basic demonstration of a thermoacoustic instability. We don't actually have a flame in here. We are going to have a hot gauze in here. I've got a gauze in there, and I'm going to heat that to make it hot. And when it's hot, we should hear the instability. So we should hear a loud booming sound. So to heat up the gauze, I'm going to use a kitchen blowtorch. Normally that's used for making crème brûlées. I'm going to use it to... I'm going to use it to heat up this gauze. So the sound that you hear is what escapes from the tube ends. I hope you could hear it. It's actually just a small fraction of the sound inside the tube. Inside the tube, it's much, much louder. It would shatter your eardrums. It's extremely loud, the sound produced by a thermoacoustic instability in a resonator. Right, so that's one type of feedback that occurs in a combustion chamber. And the other type of feedback involves a feedback between floater perturbations and sound, so sound again. And that is a rather more complicated feedback system, which depends on the exact sort of situation and exact geometries. But the same sort of instability mechanism arises in that flow perturbations enhance the sound, and the sound enhances the flow perturbations. And again, I want to show you a little demonstration. This is an acoustic resonator, a tube with one closed end and one open end, and inside is a kind of an orifice that can slide around. So by turning the tube upside down and letting the orifice slide down, I force a flow through the orifice, which creates vortices, and the interaction between the vortices and the sound inside here is what we can hear. So this is a nice little demonstration of an aeroacoustic instability. And these two types of instabilities occur together in a combustion system in general, together with even further, more complicated feedback loops that I'm not going to go into. And in this sort of combined setting where we have these multiple interactions of sound with other physical phenomena, I refer to them as combustion instability. So sound is at the center of all this, and as I've just illustrated, it sort of plays a very crucial role in combustion instabilities. Now, where do such combustion instabilities occur? I've got a few examples here. They can occur in gas turbine engines, like we have here. They can occur in boilers, like the boiler you might have in your house to heat your house. They can occur in furnaces, like is shown in this picture. They can occur in rockets. And generally, they can occur anywhere where you have a cavity with a flame inside. And what's important is that the flame is burning continuously, not sort of on and off like in a car engine, but a continuously burning flame in a cavity is basically a recipe for combustion instability. And combustion instabilities can be very destructive. This shows an example of a gas turbine that has been badly damaged by a combustion instability. So upstream of these turbine blades was a combustion chamber with an instability, a combustion instability inside, and which obviously is sort of associated with high pressure oscillations that affect the structural components of the combustion chamber, like the liner. In this case, the liner suffered fatigue, a bit of the liner broke off, and then got swept into the path of the turbines, leading to this massive damage. So that is very expensive to repair, and also in the case of a gas turbine, there's a downtime, you can't make electricity during that time, so there's also loss of income. So this kind of scenario is a bit of a disaster. And as if that wasn't enough, there's an extra difficulty, which is that instabilities tend to occur without warning. They tend to come out of the blue, literally out of the blue. Like there have been cases of possible triggers where wear and tear over a long time sort of made very slight changes to the combustion system, and at one stage, a stage was reached where a combustion instability was triggered. Noise, just noise itself can trigger a combustion instability. There was an example of a case where a change in ambient temperature, completely unrelated to what's going on inside the combustion chamber, you would think, triggered the combustion instability. And there must be other cases where the exact reason what triggered the combustion instability was never actually worked out. So what we can take away from this is that generally there is a risk of triggering a combustion instability when there is some change in the condition of the combustion system. And that change doesn't need to be big. That can be a very tiny change. Suddenly you are there with a combustion instability. Now, systems that are particularly susceptible to combustion instabilities are what I call low pollution combustion systems. So I've divided them into two groups, into reduced pollution and zero carbon combustion technologies. So reduced pollution combustion technologies, they've been around for some time. They use lean premixed flames and burn at low temperatures. And this is a cleaner way of burning. And they may also use hydrogen blend fuels because hydrogen hasn't got any carbon in it. So with these kinds of technologies, you can reduce the pollution. And with zero carbon combustion technologies, you can even sort of cut out the pollution altogether, ideally. So carbon-free fuels such as hydrogen and ammonia are currently being researched quite actively. And an alternative would be biofuels, also they are being researched very actively. Of course, the benefits of such technologies is to minimize CO2 production and also NOx production. NOx is a poisonous gas, the gas that's responsible for acid rain. So with these lean premixed flames, they minimize the NOx production. However, these benefits come at a price, the price of problems, which is an increased risk of combustion instabilities, and specifically for the case of hydrogen flames, the risk of flame flashback. And remember, it's just necessary for a very small change in some sort of operating parameter to trigger a combustion instability. So if you do something drastic, like change the fuel, you really have to expect to inviting combustion instabilities. So combustion systems and instability control strategies need to be redesigned for carbon-free fuels. Now, before I get on to the acoustics, let me say a little bit about premixed flames. What is a premixed flame? Well, we all know it from experience, but sort of in a more technical way, the flame is the visible part of an exothermic chemical reaction. So we have, to start with, before the combustion, we have fuel and oxidizer, typically that's air. They are burnt, and after the combustion, we have combustion products and light. And the visible part of this light is what's called the flame. Now, premixed flames is a special type of flame. In this special type of flame, the fuel and the oxidizer are mixed prior to combustion, and the combustion takes place in a thin interface. Now, the most basic example of a premixed flame is shown in this picture here. This shows a flame sheet in a stationary premix. So we have a tube, and we have a combustion zone, which is like a sheet across the cross-section of the tube. That was started at the upstream end by igniting the mixture, and then the combustion zone would eat its way through the unburnt mixture and leave behind a trail of burnt mixture. So in this picture, the flame has already propagated some way down the tube. So this is associated with a propagation, and the speed of propagation of this combustion zone is typically called SL, which is the laminar flame speed. And that laminar flame speed depends on fuel type. Like it's for methane, it's very different than for hydrogen. And it also depends on the ratio between the fuel and the oxidizer. Right, so the last picture I showed was the most sort of fundamental and idealized premixed flame. Let's make this a step more realistic and look at a Bunsen burner flame in a steady velocity field. So here we have the top of the Bunsen burner tube, and from below we get the unburnt mixture, and the flame in this case forms a conical shape like is drawn here, and the mixture passes through the flame sheet and gets burned, so above the flame we have the burnt mixture. And this flame is steady because although the flame sort of propagates into the unburnt mixture with the laminar flame speed SL, but the velocity of the mixture has a component which is also normal to the flame, which is U. U is the sort of total velocity, U times sine alpha, where alpha is this half angle at the top. So if those two velocities, the SL and U times sine alpha, are in balance, then we have a steady flame front. So that's what it says here. We have a kinematic balance if U times sine alpha is equal to SL, or if you solve that for sine alpha, you have sine alpha is SL over U. So that means the angle of your Bunsen burner flame adjusts to the velocity ratio of laminar flame speed over the velocity of the incoming mixture. Now, if you increase the SL, your flame becomes flatter. Well, the sign of an increase in SL means that this ratio becomes bigger, the alpha becomes bigger, that means the flame becomes flatter. So when it was like this before, it goes flatter. And the other way around, if you increase U, you increase the denominator, so you decrease sine alpha, and your flame becomes longer. Right, this is still a very idealized flame. In more practical situations, your velocity field is not uniform and steady, but it's sort of two-dimensional or three-dimensional, and it does different things at different times. So if we have a sort of multi-dimensional velocity field in this at the exit of the Bunsen burner tube, that distorts the conical flame front and introduces these wrinkles, and these wrinkles then travel up the flame, and the whole flame sort of changes shape all the time. Now that's important because the flame surface area is proportional to the heat release rate. So if your flame changes shape, and with that it typically changes the surface area as well, that means the heat release of such a flame oscillates. Right, so that was a very sort of quick crash course about flames, what we need in terms of combustion instabilities. I now come to part 2 of my talk, which has a title, Modeling Combustion Instabilities with a Green's Function Approach. So there are lots of approaches to model combustion instabilities. There are experimental approaches, numerical approaches, and analytical approaches. My speciality is in analytical approaches and sort of slightly numerical, but not a lot, to understand sort of the physics behind what we are modeling. And I use a Green's function approach, which I'm going to explain in this part. Now let me sort of outline the mathematical modeling approach. The basic idea is actually very simple. So we have a combustion system, and I break that into 2 elements. The first element is the acoustic resonator, and the second element is the unsteady flame. And those 2 elements I'm going to, sorry, I need something to drink. Those Right, those 2 elements I'm going to treat separately at first and then combine them later. So the acoustic resonator I'm going to model by a tailored Green's function. I'm going to explain that in the next few slides. And the unsteady flame I'm going to model by an amplitude-dependent transfer function. And again, I'm going to give some more detail on the next few slides. So I have these 2 separate models. And then I'm going to use a Green's function approach again to combine those 2 elements to model the complete system, the combustion system. Right, now what is a tailored Green's function? The tailored Green's function describes the acoustic resonator, and I'd like to illustrate that with this picture here, where we have a kind of a generic combustion chamber. We have a cold section and a hot section, an inlet. There may be a blockage in there, there may be an area change, and then in between these features we have sort of one-dimensional conditions. This is the kind of combustion chamber I'm considering. Right, but no flame. We are just modeling the acoustic resonator here. Instead of a flame, we have a hypothetical point source, which is marked by this star shape. So that point source fires an impulse at a particular time, which I call the source time. So this is the pressure impulse. It's fired at a point x star, which is the location of the point source, at time t star, which is the firing time. And then, in the same combustion chamber, we have an imaginary observer who sits here. And this observer measures the response at their position x and at their time t. So what this observer measures is the impulse response of the resonator. That's the physical name, impulse response of the resonator. And tailored Green's function is exactly the same thing. It's basically a synonym of impulse response, but it's the term that mathematicians tend to use. That's the mathematical term. Now, the tailored Green's function is a superposition of modes. Remember, we are inside an acoustic resonator. So what does the tailored Green's function look like? This is the notation, so it depends on observer point, source point, and then the time difference between observer and source time. Now, before the impulse, nothing is happening. The Green's function is 0. That's how it should be, because otherwise we would violate causality. After the impulse, the Green's function is given by a superposition of modes. N is the mode number. The omega n's in here are the eigenfrequencies of the acoustic resonator, and those gn's here are the Green's function amplitudes. So we have a superposition of modes with individual amplitudes and individual frequencies. And if we know the amplitudes and the frequencies, then we have the Green's function. And in fact, these can be calculated analytically, the GNs and the omega n's, for the kind of quasi-one-dimensional geometries that I've shown in the previous slide. For this kind of geometry, we can calculate them analytically. For any geometry, in principle, they can be measured. Remember, all we are measuring an impulse response. We need a point source that fires an impulse and an observer. Right, so this is how we model the acoustic resonator without the flame. Let's now turn to the flame. And the unsteady flame we are going to model as an input-output system. I'll show it first in the frequency domain. So here in red, we have our flame, which will describe our transfer function. I've called that T of omega. The input is a velocity field, with a mean part u bar and of frequency omega. So the amplitude, it's a complex amplitude u hat of omega, and this is the time dependence. So that is the input, it's a velocity, and the output over here is the heat release rate, which has the same frequency omega and some mean value q bar. And the flame transfer function is defined as the ratio of output over input. And both the output and input are normalized by the mean quantities q bar and u bar. Now, this works fine if you are doing sort of low amplitudes and are just interested in linear phenomena. But if you're also interested in what happens if I have very high amplitudes and if I want to study nonlinear phenomena, this isn't good enough. You need to know what happens at high amplitudes. And this is where the flame describing function comes in. The flame describing function is basically a set of flame transfer functions at different input amplitudes. So it depends not just on the frequency, omega, but also on the input amplitude, A. And this flame describing function can be obtained in various ways. For linear flames, linear laminar flames, it can be calculated analytically. For nonlinear flames, it can be calculated from the same basic equation as here, which is a level set approach, but it has to be calculated numerically. It's too difficult to solve analytically. And then it can be calculated also numerically from combustion CFD with relatively high effort and also varying amounts of effort. Some are more high fidelity than others, some numerical methods. And of course, it can be measured for many flames, and that has actually been done. Right, so this is how we can describe the flame in the frequency domain, but we can also describe it in the time domain. So that was our frequency domain description. I've just changed it slightly, so I've written it in this form: Q, the output equals transfer function times input. And if I write it like this and then apply an inverse Fourier transform, I get into the time domain with this expression for the fluctuating heat release rate, Q dashed. It's a convolution integral with time integration variable tau. So that sort of includes the velocities at earlier times. This h of tau is an impulse response. That's a different, not the Green's function, but it's the impulse response of the flame, and you get that mathematically from the inverse Fourier transform of the flame transfer function. And just to give you an idea of what a flame's impulse response looks like, I'm showing this graph down here. So as a function of time, the red curve shows an impulse response. It typically has a couple of maxima, a couple of minima, and where the peaks and troughs are characteristic times, tau 1, tau 2, tau 3, and these times tend to be associated with sort of propagation processes along the flame front. Right, so we have described the acoustic resonator by the Taylor-Green's function. We've described the flame by its transfer function or impulse response. Now we have to put the two things together, and I'm going to do that with a Green's function approach. So a Green's function approach combines the resonator and the flame. Now I'll just state the governing integral equation, which is written here. uq is the velocity at the flame, and that is given here in terms of a time integral, and q dashed is the heat release rate, and g of t minus t star, this is my Taylor-Green's function. Now, it's possible to derive this integral equation from first principles, which is quite a lengthy mathematical process. I don't want to do that. What I want to do instead is give you a kind of physical interpretation of what this equation means. Right, so let's imagine we have a heat release impulse which fires at a time t1. And the peak value of this impulse is q1. Now we have an impulse, so the response to that impulse will be the Green's function multiplied by this peak value q1. And the impulse response is shown here by this blue curve. So nothing happens until the impulse, so we have 0 response, and then we have a superposition of modes after that. Okay, now generally we don't have an impulsive heat release rate. We have a sort of some kind of time history. The heat release rate is described by some kind of time history. I'm losing my pointer. Like this curve, any sort of a continuous curve. And that you can approximate as a series of tightly packed impulses at times t1, t2, etc. And then you can the first impulse produces a response that we've just seen up there. The next impulse produces a response which is q2 times g of t minus t2, and so on. So you can add up all the responses of the individual impulses to get this sum, and here is the corresponding time history. Now, if we have a closer look at this sum, all this is the discretized version of this integral here at the top. So that's what's behind this integral equation. And this integral equation is very convenient because it's so easy to solve. It can be solved with a very simple time-stepping method. You can write your own code. You don't need any sort of fancy software or anything. Yeah, so to do that, you perform an iteration process and you get the time history of the velocity at the heat source and of the heat release rate Q. So let's say we have an initial value for the heat release rate, and then we know the Green's function, we know everything about the Green's function. Then you can evaluate the velocity at the next time step, t plus delta t. Once you have the velocity at the next time step, you get the heat release rate with our model for the flame. You get the heat release rate at the next time step. And then you go back to this equation and you sort of iterate yourself forward in time and get a time history for the velocity and for the heat release rate. Right, so this is my modeling approach, and I have used that with various postdocs and PhD students, past and present. And you can do some really nice predictions. You can get some really nice predictions from this approach. And I would like to show you a few examples in this third part of my talk. Right. I've done some work with a postdoc called Alessandro Bigongiari, who used the Green's function approach to predict limit cycle amplitudes and also hysteresis. Now, she used this approach of dividing the system into an acoustic resonator and a flame. The acoustic resonator in Alessandro's case was a tube with open ends, in other words, a half-wave resonator. And the flame was described by a nonlinear time lag law, which is given up here. So on the left, we have the heat release rate. And on the right, we have two velocity terms. This is a time-lagged velocity term with time lag tau, and this is a sort of velocity term at the current time. And then we have two coupling coefficients, N1 and N0, and these three quantities that are sort of marked by these gray rings, the N1, the tau, and the N0, they are amplitude dependent. And where does this heat release rate law come from? It's a law that I have guessed from experimental data that was produced by Nicolas Noret, who is also part of this conference, in his rather nice PhD thesis. Anyway, so we have a sort of somewhat realistic heat release law and a simple acoustic resonator, and then through our Green's function approach at this problem, to see what we can predict. And we can predict several things. We could predict a stability map, which is a map where we have a control parameter. In this case, the one that's shown here, the control parameter is XQ, which is the position of the heat source or the flame inside the tube. The tube was 2 meters long. So from 0 to 2, that was the length of the tube. And the position of the flame could be moved all along the length of the tube. And on this axis, we have the amplitude. Sorry, this axis here is the amplitude. So this is a stability map showing stable and unstable regions. The white regions are stable, the gray regions are unstable. So if we perform our time iteration, starting from a fairly low amplitude, which corresponds to this point in the stability map, at a flame location of 1.47 meters it was, we get this time history. So that's the starting amplitude, and we see we have sort of an exponential growth at first, that slows down, and very soon reaches a limit cycle. So that's the kind of prediction that can be made with the Green's function approach. And this is completely coherent or in line with the stability map. So in the stability map, the corresponding trajectory is shown here by this blue arrow. So we have an unstable oscillation. The amplitude rises, rises, rises until it hits the boundary of the unstable region, and then the amplitude stays constant, and this is where we have the limit cycle. Right. On top of predicting limit cycle amplitudes, we can also predict a hysteresis-type behavior from this stability map. So this is the same stability map that I've shown on the previous slide with the location of the flame as our control parameter. And hysteresis means if I change this control parameter in one direction and then change back in the other direction, different things happen on the two paths. And that's indeed the case here, so let me show that here. Let's start at the downstream end, with the source at the downstream end, and we move that towards the middle of the tube, the center of the tube. So amplitude is 0 here because we are in a stable region. Then we hit the border with the unstable region. So our system becomes unstable, the amplitude increases until the top of the unstable region. And if we move XQ further towards the center, we go along this trajectory. Now, before we reach this point where all these gray areas meet, let's go back with our XQ and move it back to the starting point. So here the two curves overlap, but there's no reason for the system to sort of decay in amplitude. It just stays up there, and the starting point was here. So the backward path and the forward path are clearly different, and that indicates that we have hysteresis. And if you want to know further details about this piece of research, we've published that in a JFN paper. Right, the next piece of work I want to show you is one I have done with another postdoc, Srinath Malaman Gopinathan. He considered an acoustic resonator which is more complicated than the one Alessandra had, and he also considered a more realistic flame. Right, so the acoustic resonator is depicted here. It has a cold region and a hot region, closed end on the left, open end on the right, and also a perforated plate. I think this pointer is sort of losing its power. A perforated plate here. And that perforated plate acts as an anchor to the flames. So there are little flamelets sitting downstream of each hole in the perforated plate. So that's the acoustic resonator Srinath has considered. And the flame he's considered was a hydrogen-enriched flame, a hydrogen-enriched methane flame, with a laminar flame speed that depended on two factors, hydrogen concentration and equivalence ratio. And that dependence is shown in this graph here. The dependence on the equivalence ratio, you can see sort of, it's not very strong. Okay, it's not exactly constant, but there's nothing mad happening. However, if you look at the dependence on the hydrogen concentration, so this is for low concentration, 0%. The first four more or less overlap the first four curves. But when we come to 60%, that's represented by the blue curve, you can see that the laminar flame speed, which is plotted along this axis, is distinctly higher. That's for 80%, that is higher still, and that is for 100% hydrogen, that is way above the case for no hydrogen. So the hydrogen concentration has a very strong effect, especially at higher concentrations, on the laminar flame speed, and that dramatically changes the dynamics of the flame. Right, Srinath has also calculated the impulse response of the flame for different amplitudes, or rather, I should say sort of correctly, the inverse Fourier transform of the flame describing function for different amplitudes. The lowest amplitude is shown here by the red curve, and then this is for 0.02. It's a normalized amplitude, so it's amplitude over mean velocity. Just think of the mean velocity as 1, and then the epsilon gives you the amplitude. Okay, so this is 0.02. Then for epsilon equals 0.2, we get this blue curve, which is distinctly different, and this peak so shifts to the left, and it shifts further to the left as we increase the amplitude. So the amplitude has a strong effect on the behavior of the flame. Anyway, there's a lot more detail to be said. I can't fit that into this talk, but I want to show you the sort of final result of this study, which is a three-dimensional stability map and flashback map. So the two control parameters were the equivalence ratio along this axis and the hydrogen concentration on this axis, and here we have the amplitude on this axis. So that blue surface shows the kind of boundary between unstable and between the unstable region, which is below it, and the stable region, which is above it. And this, this red surface shows the boundary between the stable region, and flashback. So as you can see, as the hydrogen increases, the hydrogen percentage increases, the flashback occurs at lower and lower amplitudes, which is exactly what you expect because hydrogen has this very high laminar flame speed. And again, you can, we have published this work, and you can read up about it. Now, the next piece of work was done by Ashwati Surendran, who was a PhD student of mine, and she studied passive instability control in a boiler. So the acoustic resonator she considered is shown here. We have a cold region, a hot region, and a cold region. And separating the first cold and the hot region is a flame, and separating the hot region from the second cold region is a row of heat exchanger tubes. So these heat exchanger tubes cool down this hot flow. That's why we have a cold region again. Right, and then at the downstream end, we have a piston which can be moved in order to sort of vary the length of this cavity between the heat exchanger and the piston. For the flame, Ashwati just modeled this by a very simple transfer function, linear with a single time lag. The heat exchanger was the tricky thing to model because the heat exchanger plays two roles in this setup. First of all, it acts as a heat sink, and secondly, it acts as a sound scatterer, because if everything was sort of uniform temperature here and you send a sound wave at this row of tubes, they will get partly reflected, partly transmitted. So both these physical phenomena were taken into account and modeled separately. The heat sink was modeled in terms of a heat transfer function, and that was calculated by combustion CFD, not combustion, by CFD. And the sound scattering aspects of this heat exchanger tube row was calculated analytically with a quasi-steady approach. Oh, sorry. And as you can see, there are plenty of things, plenty of parameters you can vary in this setup. You can vary the position of the heat source, you can vary the length of this cavity, you can vary the spacing of the heat exchanger tube. There's umpteen scope, lots of scope for parameter studies, and I've listed a few obvious ones here. The cavity length, the flame location, the mean velocity, U bar, the temperature difference, the tube spacing, and more. And here are some results focusing on the first three parameters. So along this axis, we have the cavity length, and along this axis, we have the flame location XQ. And the gray, these are again stability maps. The gray is the unstable region, the white marks the stable region. And we have three pictures here. This one is for the lowest mean velocity of 0.5 meters per second. Then we increase the mean velocity to 1 meter per second, and here it's been increased even further to 1.5 meters per second. And if you look, it's very clear that the unstable region has become smaller and the stable region has become larger by increasing the mean flow velocity. So that indicates that you can indeed change parameters to enhance stability, or if you wanted to do the opposite, you can do that as well. Yeah, and further details can be found in our International Journal of Spray and Dynamics paper of 2018. Right, the last example I want to show is with my current PhD student, Sadaf Arabi, who is looking into the effects of noise on instabilities. Now, she's studying a very similar system, or basically the same system as Alessandra Bigonchari. So she's again looking at this simple, as an acoustic resonator, which is a simple tube with open ends, a half-wave resonator, and a flame described by the same nonlinear heat release rate law with amplitude-dependent parameters N1, tau, and N naught. And on top of the heat source, there's a second source, which is a noise source in her model. That noise source emits pink noise at various levels, and we measure the level of the noise by beta, a parameter that we've called beta. Beta equals 0 means no noise, and increasing beta means increasing noise. Now here we have the stability map of our system, and Sadaf has picked a point here in this stable region, this blue point here, which is rather close to the boundary with an unstable region. And then, so this is a point with an initial amplitude of about 0.2 and a flame location of around 1.8. And she has sort of performed this time-stepping iteration that I've described with the Green's function, with a flame as a noise source and that, with a flame as a sound source and that noise source, and varied the level of noise. And I'm going to show you some time histories to show you what happens for the different levels of noise. So here are some time histories for different levels of noise. This one, the blue one, is for the case without noise. And since we are in a stable region, we expect a stable oscillation, which is exactly what we've got, an exponentially decaying oscillation approaching 0 amplitude. Now, we apply a fairly low level of noise and pink noise, and so we get this curve. It just shows the envelope, really. You can't sort of make out the individual oscillations easily, but they are there. And yeah, the sort of overall trend is still there. We have a decaying oscillation, but it looks more messy. We have sort of residual noise at later times when the oscillation should have died down completely. Now, increasing the noise level further to beta equals 4 gives this kind of time history. So we have what's called an intermittent case. So we have these intermittent bursts followed by sort of quieter periods. But it's not an unstable case. It's not a sustained instability. And finally, if we increase beta further to 6, then an instability gets triggered. Note that the scale on this axis is different from the other three pictures. So we apply a lot of noise, a high-level noise, and instead of sort of staying constant or just decaying, it goes up into limit cycle at an amplitude of about 1.3. And that is exactly consistent with this stability map. So beta equals 1, we're just hovering around in this stable region. Beta equals 4. I'm not quite sure whether we touch this region, this unstable region or not. This is hot off the press, these results. But for beta equals 6, the system gets kicked into this unstable region, grows in amplitude until it reaches a limit cycle there. Right, Sadaf Arabi is actually one of the ESRs or PhD students in my Polka project, and I'd like to tell you very quickly about it. Polka is an acronym which stands for Pollution, Know-how and Abatement. It's funded by the European Commission under the Horizon 2020 framework. It's a Marie Curie ITN with a total budget of just over 4 million euros. And this is the duration. So we started in 2019, and we are going to finish in July 2023. So it's a project of 4.5 years. We have a project website, which is here and contains a lot of information. So if you want to know more, that is a good place to look. We have a total of 16 network partners, mainly in Europe, dotted around in Europe, but there's also a partner in India, and a total of 15 PhD positions dotted around in Europe, and Sadaf Arabi is one of those PhD students. This is our Polka logo with polka dots. And the aims of Polka is to gain insight into hydrogen combustion instabilities. So we are going to have a dedicated Polka session at this InterNoise conference on Tuesday, day after tomorrow, the 23rd of August, from 8 o'clock in the morning until 10:20. There will be something like 8 or 9 talks by fellows, by PhD students of the Polka network talking about their work. Right. So that finishes part 3 of the model predictions, and I now come to the conclusions. 2 conclusions, basically. The first is I want to advocate the Green's function approach. The Green's function gives physical insights into, as we have seen, nonlinear dynamics, such as limit cycles and hysteresis, into instability and flashback of hydrogen flames, into potential strategies to control combustion instabilities, into noise effects on combustion instabilities, and more. So watch this space. It's a very, very useful modeling tool. And the other takeaway message I want to give you is that sound plays a key role in combustion instabilities. Without sound, life would be so much easier when it comes to designing combustion systems. But sound really throws a spanner into the works. And for that reason, sustainable combustion technologies need acoustics research. And with that, I've finished. Thank you very much.
Thank you very much, Maria, and I thoroughly support your efforts to promote analytical modelling over other types of modelling, which can be much more black box and can result in bridges falling down. But let's ask for some questions. If you want to ask a question, please move yourself to a location near a microphone. I can't see much movement, and I can't see any questions from our virtual or online audience either, so I'll have to ask one. So one of the things that we're being persuaded to do by our government is to stop using our domestic gas boilers. This is an attempt to get towards net zero, and instead have ground source or air source heat pumps. But when I discussed this with the gentleman that came to service my gas boiler, he said it'd be much cheaper for me to get one that would be convertible to hydrogen. And so my question is, does any of your research indicate whether or not that's going to result in noisier or less noisy or more stable or more unstable combustion?
Oh,
sorry,
can I answer that question first?
Can you find a microphone for your question?
I'll answer that question first.
Yes,
Okay, right. One of the Polka partners is a company called Beckert. They produce the sort of burner part of domestic boilers. And they are actively working on designing a boiler which can run on any concentration of hydrogen, from 0 to 100. But this is in development. This is, I don't know how long it takes, but there are certainly activities going on that very front.
Thank you very much. Now we have our question next to a microphone.
Please, congratulations to your exposition. I am Shaya Ackerman. I am an engineer, mechanical engineer of Brazil. And I had some experience by furnace. And I asked a simple, why the temperature was not considered in your studies?
Why temperature was not considered in
why the temperature was not be considered in these studies?
But I did. Oh, I can't go back anymore. I'm not sure whether you heard the whole talk, but I considered, like for example here, we considered this kind of acoustic resonator with cold, hot, and cold regions. So the temperature is in the model.
Because different temperatures can affect the result.
That's right, absolutely, yes. All I didn't do is I didn't show any results for temperatures. I had to be very selective.
Okay.
Thank you very much. Is there another question behind you? Or not? Sorry, the gentleman just stood up. Do you want to ask a question?
Thanks, Maria, for your nice presentation. I have a question. I have actually two questions. The first question is the advantage of gain function against network modeling. And my second question is that how we can use the gain function to deal with non-planar acoustics. Because I think the results showed in all cases 1D acoustics. But my question is that when we are in really high frequency and considering the plane wave is not really it's not really happening, how we can use gain function to deal with this problem?
Right, I'll answer your first question first, and then I'll come back to the second one. So the first question was, what is the advantage of using the Green's function as opposed to network modeling? Right, I've had this question before. The two give the same kind of results, but the Green's function is more easily extended to multiple sources. So if you have your tailored Green's function for a system like this, and you want to investigate what does noise do to the system, you just add an extra source. You have your tailored Green's function, that's it. You add an extra source, and you can very nicely extend it. That's one advantage, so there's a flexibility of it. Another advantage is you can really handle nonlinear problems. So in the cases that I have shown, where you have a flame describing function with amplitude dependence, you can sort of still do that with network modeling. It's a bit clumsy, but it works. But if you have a truly nonlinear heat release rate law, like, I don't know, Q depends on the square root of the velocity, then network modeling has reached its limit. With a Green's function, you can tackle that one. And I'm afraid I've forgotten your second question. Can you repeat that, please?
If I'm correct, the gain function, tailored gain function you obtain is it was 1D, no, just in a space, the 1D acoustics. Okay, we are acousticians, so we are used to here. My second question is that I think in the result and the former research, the acoustic domain was a plane wave actually in all of them. So and my question is that how we can deal with on-plane wave acoustics in acoustic domain.
Okay, so the kind of resonators I have shown here were all sort of one-dimensional or quasi-one-dimensional. So you could break them up into one-dimensional chunks and then stitch them together. There are Greens, you can calculate the Green's function for example, annular combustors as well. So you have a cylindrical tube with a smaller tube inside, and you can analytically calculate the Green's function for that. It's a bit of a job, but it's doable. Or another case, a sort of rectangular combustion chamber, like a box. The Green's function for that is also known. But for more complicated geometries, I'm not aware of anybody who has calculated the Green's function. But in principle, you could measure it.
Yeah. And if in the case of an unplanar wave, I think in thermoacoustics we need to couple the Heckl with the upstream acoustics. I think in thermoacoustics, to do the stability analysis, we need to couple the Heckl to upstream acoustics. And in this case, in which point we want to couple, because on the acoustic it doesn't matter, because if you choose every point, it's still plane wave. So the coupling is happening. But when we are dealing to non-plane wave, I think the coupling between the flame and the acoustic domain, maybe it's a bit challenging, at least what I'm thinking at the moment.
It's certainly a lot more complicated. I dare not speculate at this point how you would do it, so I'm afraid I have to pass on that one.
Thank you. Thank you. It was an amazing presentation. I enjoyed it.
Thank you.
So much.
And please, can we thank Maria again? So now I think it's the social hour, is that correct?
Not quite yet. Just about. You're obviously very keen. Very privileged, and I'm pleased to introduce to you Jacqueline McLaren, the Right Honourable Lord Provost for the City of Glasgow, Convener of Glasgow City Council and Lord Lieutenant of the City of Glasgow. Just by way of explanation to our international guests, it's a bit like the Lord Mayor, but for the City of Glasgow. Jacqueline McLaren.
Thank you very much, everyone. I do have to make a slight apology. I am not Jacqueline McLaren, the Lord Provost. I'm Bailey Linda Pike. I'm here deputising on behalf of the Lord Provost this evening, but I hope you're not too disappointed. I'll try my best. Ladies and gentlemen, on behalf of the Lord Provost and the City of Glasgow, I want to wish you a very warm welcome. We're gathered here at this hugely successful Scottish Events campus located on the banks of the River Clyde, a river that's synonymous with the city, its history, its fortunes and its people. A river that's part of our DNA, if you like, which allowed merchants to buy and sell and others to travel to far-flung parts of the world. Proud Glaswegians who took their wit, wisdom and learning across the globe. I'm sure you'll agree it's wonderful to be able to get together in person as we move through this pandemic. A pandemic that has profoundly affected us all on a personal and professional level. It's also my opportunity to thank you on behalf of the City for your important work surrounding acoustics, noise control and engineering. We're all affected by noise and vibrations. Its presence is pervasive, inside and outside, in our homes, the workplaces, parks, communal areas, shopping environments, and in the streets and communities. As you all hopefully know, noise can be beneficial and enhance our lives, like listening to our favourite bands or composers, some of whom you might actually have seen live here in this event. And of course, the calming sounds of nature, like the sea, the streams, birdsong, which apparently, I have just found out, is commonly known as pink noise. I was intrigued to learn there is a whole colour spectrum of noise. I did know about white noise. I had never heard of pink noise, brown noise or blue noise, and much of which is detrimental to our health and well-being. From the noise of antisocial neighbours, and in a city like Glasgow with a high prevalence of communal living in tenements and high-rise flats, this is a reality. There's also issues like dogs barking, living next door to hotels, entertainment venues, takeaways, and the incessant noise of phones ringing everywhere. And for a city like Glasgow, with a proud naval and maritime history, it's particularly relevant that conference will also be discussing ship and offshore acoustics, as well as aircraft noise. I reckon everyone here would agree the impact of noise pollution is a real and growing area of concern. That's why it's vital you hold events like this InterNoise2022 51st International Congress and Exposition on Noise Control and Engineering to give this important subject a global platform. I understand a recent survey on the economics of the UK acoustics industry showed it contributed £4.6 billion to the UK economy and employs around 16,000 people in small and medium enterprises across the UK. Your conference theme, Noise Control in a More Sustainable Environment, is relevant and necessary as we all re-evaluate how we wish to live and work. Glasgow is thrilled to be hosting this international event that's attracted more than 1,000 of you delegates from more than 40 countries, and the majority of you have elected to attend in person. That is fantastic news, particularly for the students and early year professionals who will benefit the most from these kinds of events and networking opportunities. For those of you unfamiliar with my city, I'm confident you will enjoy your stay here, thanks to Glasgow's reputation as a friendly, fun and hospitable place, a reputation our citizens, the people who make Glasgow, have worked hard to earn. This is also a place with a wealth of culture and entertainment. Please enjoy your conference and the city's hospitality. I trust you will leave with fond memories, and remember, keep it fun and keep the noise down.
Thank you very much. I'm going to make this very short, so I'm just going to forget what I've got on my pages here. It's great to have a leadership in Glasgow City Council that very much focuses on the sustainability of the future, and if you go through the Glasgow City Council web pages, you will see all the work that they're doing in terms of trying to meet the challenges of a sustainable future. But what you finished with there was the friendliness of Glasgow. And certainly if you go out to Glasgow and take the chance to see some of the beautiful architecture and the buildings that are there, and you find yourself looking up at the buildings, somebody will come along and speak to you. And that's normal. So we'd like you to be honorary Glaswegians when you come here, or Ouijies, as is the term that is colloquially known as a Glaswegian. And speak to your neighbours and your friends and colleagues at the conference here. Make them feel at home, and we hope you have a wonderful conference. Thank you very much to Glasgow City Council. Thank you for your leadership in sustainability and in terms of the way you take your decision making and policy making. And thank you for supplying the drinks reception that we are now going to enjoy. Could we say thank you again to Glasgow City Council? Barry, the drinks reception is in the exhibition area. So make your way to the exhibition area and we will enjoy ourselves meeting there. Thank you.